So let us start with small signal model of PN junction. So write down this small signal model is actually an equivalent circuit. It is an equivalent circuit of PN junction diode under small signal conditions. All right. So equivalent to this PN junction, this is the symbol of a PN junction. This is anode and cathode. So this is represented by, first of all, diffusion capacitance, which is active in the forward bias region. Then we have depletion capacitance, which is associated with reverse bias PN junction, C dep. Then we have diffusion resistance. This I will talk about today. And then we have series resistance, RS. So this is P, this is N, this is RD. This is your PN junction symbol, and this is your small signal model. I'll explain each of them again. First, you draw it. Small signal model of PN diode. Alright. The voltage across these three is VA, and the total voltage from here to here is V applied. So basically V applied will be VA plus, if a current flows through this resistor, it will be plus I into RS. Now this is your IR drop. IR drop in the neutral regions. Okay, please note it down. Here RD is the small signal forward resistance. So whenever the diode is on, it will give exponential rise in current with response to the voltage, right? So in the forward bias, your diode will have a very small resistance, which is RD, which is dependent upon forward applied voltage. So write down over here, RD is diffusion or small signal forward resistance. Here C diffusion is the diffusion capacitance. So in the last lecture, we have discussed about diffusion capacitance and how it reacts to the forward applied voltage. And then third one will be C depletion, which is depletion capacitance. So this corresponds to the behavior of PN junction under reverse bias. And the last one is RS. Now RS is the series resistance of the combined N and P neutral junctions. You know, PN and neutral junctions are there apart from your depletion region. So that also corresponds to certain resistance, which is series resistance. This is series resistance. So this is combined N and P neutral region resistance. All right. So kindly note it down. So basically in all the analog circuits where the signal is analog, your circuit behavior is determined by how the PN junction diode reacts to the small changes in the diode voltage and how does it produce the diode current. So why these models we study? Because these models we can build up in your spice engines, and whenever we add a diode internally, this model is running. All right. So now we'll try to derive the formula for the small signal. What do you mean by small signal? Small changes in the applied voltage. All right. And it's basically an approximation. Completed this? All right. So what I was saying was, so we'll have a PN junction, and let's say we have forward bias it. So what is small signal means? We'll change V from V to dV. Small changes in V, and it will lead to current plus delta I. Yes or no? So if you apply voltage, certain voltage, you'll get a certain amount of current. Yes. So if you apply incremental voltage, you'll get the incremental amount of current. Yes or no? And since diode can also be treated as a capacitance, voltage corresponds to change in charge across the depletion layer. All right. And if you have an incremental voltage, it will lead to incremental change in charge also. And that is what C is. Capacitor is dq by dV. Change in charge upon change in voltage. That is why the concept of capacitance comes. How the diode will act as a capacitance. So in this small signal model, we are making a small change in voltage and we are estimating the charge changes in the current and charges. And we have to give them sufficient time for them to settle down. Yes or no? Because if we apply voltage, change in the charge will take some after certain time. All right. Change in the current also will take after certain time. So we have to take care of that for the effect of changes to stabilize. So let's say this 2 volt is changed to 2.1 volt. So this is increment is 0.1, right? It will take some time for this. Let's say this is 2 milliampere to become 2.1 milliampere. Understood what I'm saying? Similarly, it will take some time for the charges to build up. So we'll now analyze every component of small signal model. So let's analyze the first component, RD. What is RD called as? Diffusion resistance or small signal forward resistance. So it is diffusion resistance. Now, do you recollect this forward characteristics of PN junction? So it is a graph of current versus voltage. All right. Applied voltage versus circuit current. So this is how the graph will look like, exponential in nature. Yes or no? And we know this relationship between I and V. So this is applied voltage. This is the diode current. So what's the relationship between them? I naught exponential of VA upon VT minus 1. Yes or no? We have derived this equation. Now, if we are considering a small signal model, we have to consider a small segment of it. So small segment of this exponential curve will be a straight line. Yes or no? So let's say this segment from here to here is a straight line. So we take a tangent to this, and wherever this small uh, section which is linear is a straight line, we check the change in the voltage and change in the current. So this corresponds to change in voltage. Okay, and this change corresponds to change in current. Yes or no? So now if I take the differentiation of this did by dVA with respect to VA voltage, it will be I naught. What is exponential of x or 2x? E raised to 2x, derivative of that, e raised to 2x into 2. Correct? So here I naught is a constant. So what is the derivative of e raised to VA upon t? E raised to VA upon VT divided by VT, because it is divided. And this minus 1 will disappear because derivation of a constant is 0. So this is what you will get. Yes or no? assuming that I is very much greater than I naught, because I naught we consider to be constant. Now, this dId by dA is nothing but 1 upon Rd. So this is Rd, which is nothing but delta Va upon delta Id. Okay, so this I can write it as 1 upon Rd, yes or no, is equal to, what is this? I naught into A raised to Va upon Vt. This is nothing but I only, na? Diode current only, divided by Vt. What is Vt? Thermal voltage. Thermal voltage, Vd. So what is the formula for Rd now? It's Vt divided by the diode current, the DC diode current. So more current you have, the resistance will be less. Inversely proportional, no? And this is valid for forward bias. So this is called as small signal forward resistance. Small signal forward resistance, or forward bias resistance, or diffusion resistance. So what is the conclusion we draw over here? As VA increases, yeah, what will happen in forward bias? ID will increase, and as ID increases, what will happen to diffusion resistance? It reduces, and vice versa. That means if you decrease the forward applied voltage, current will decrease and resistance will increase. Acha, what about reverse bias? For reverse bias, what is current given by? Minus I naught. Yes or no? So in this case, since the current is very, very small, what about this diffusion resistance? It is infinite. Got it? So this is for ideal reverse bias diode. Practically, it's very large value in reverse bias. So practically, in real diodes, RD is in the range of few hundred kilo ohms to 300 kilo ohms. Okay, for real diodes, which we practically use. All right. What happened? Any doubt? R RB is reverse bias. FB RB is forward bias and reverse bias. Okay. So this, if they ask you write a short note on small signal model of PN junction, you have to draw the model and explain every component in it. Can we go to the next one now? Second component. So write down, second component is diffusion capacitance, CDEF. Okay. So listen to the statement which you need to write. So I'm not writing it right now, I'm just describing it. It's 2 lines will come over here. In a forward bias PN junction, listen to it. This I have already explained, but still I'll repeat. In a forward bias PN junction, large number of carriers are stored on the two sides of the junction. Yes or no? Remember, in a forward bias PN junction, large number of carriers are stored in the either side of the junction due to diffusion of carriers across the junction. Yes or no? Because the carriers, majority carriers flows to the minority region, and minority carriers from majority carrier from N side also flows to the minority region P side. So large number of carriers are stored. So as we go on increasing the or decreasing the forward applied voltage, there is a change in the stored carriers, and that will represent the capacitance, because that is representing charges, right? So there is change in charges with response to change in voltage, and that is representing diffusion capacitance. All right. So due to diffusion across the junction, these carriers are stored outside the depletion region. All right, which give rise to diffusion capacitance. So write down diffusion capacitance is dominant under forward bias and is given by, now this you don't have the derivation for it, C def is equal to I d tau s upon Vt. Okay, tau s is the storage time. And this value is very, very small. Normally, diffusion capacitance is in the range of nanoamperes, nanofarads. Normally, capacitance start from microfarad, right? But their ranges are in nanofarad. What happens in reverse bias? There is no diffusion of carriers, no? So in reverse bias, C diffusion is negligible. It only happens in the forward bias due to diffusion of charge carriers across the junction. Okay? Yes? Now we'll go for the third component, C depletion. So write down depletion capacitance. All right. So we have a PN junction. This is my PNN. And what is this? I have drawn depletion region. So the origin of these capacitance comes from the presence of uncovered positive and negative charges on both the sides of the junction. So what do you mean by uncovered? Meaning, if I apply a reverse bias to it, like this, reverse bias. If I increase reverse bias, what will happen now? This depletion region will be expanding, right? That means we are uncovering these charges, right? Yes. So depletion region will widen. That's the other way of showing that it's uncovering these positive and negative charges, which were not present first. Now they become immobile. So there is a change in the, so what happens is this acts as a capacitor. So this is one plate, this is second plate. In between we have the depletion layer. So what is changing? The width of the depletion layer is changing. So the distance between the two parallel plates is changing. Are you getting it? That is the origin of depletion capacitance. Got it? So VR changes, W changes. Okay. So as the reverse bias voltage increases, more such charges are uncovered. That means your depletion region width is increasing, which will give rise to diffusion capacitance. And this diffusion capacitance is given by epsilon A by W. It is resembling the parallel plate capacitor. What is the parallel plate capacitor formula? Epsilon A by D. Remember? Yes or no? So your D is distance between the two plates is nothing but width of the depletion layer. So the C depletion is dominant in forward or reverse bias? This is dominant in reverse bias. In forward bias, C depletion is negligible. So in forward bias, C depletion is negligible. All right. The fourth component is series resistance. Completed this? Completed? So let's talk about the fourth component, series resistance. RS. Okay. So in this PN junction, if this is my depletion layer, what is this? N and P. This is N neutral, P neutral. Why we call it neutral regions? Because the fields are not present over here. Yes or no? But these regions are also made up of semiconductor. They will have resistance. So there will be resistance over here. Here, entire region mein. Got it? There will be resistance over here. Yes? And that combined resistance we call it as RS. Understood? So write down in a PN junction, the neutral N and P regions have finite resistance. Okay, so we combined it, called it as RS. We combine both the N and P region resistance and call it as RS. Okay, understood or no? Now we'll summarize the entire model. Yeah. So let's summarize the entire model. Now, let's draw the small signal model in forward bias only. So what this will contain? It will contain RD and C diffusion because these two are dominant, not there. Acha, what is RD value? VT by ID. Yes, this is in millivolt. This is in milliampere. So this will be few ohms, which is very small. So basically the value of RD will be small. Yes, this is PN junction. And what else will come over here? C diffusion. It is given by I tau s upon Vt. This also is very small in nanofarad. But the question is, why they are connected in parallel? Come on, tell me. Why they are connected in parallel? Why RD is not connected in series with C diffusion? The answer to the question is because the same voltage is applied to PNN in forward and reverse, right? Across, now we applied across. So since we apply the voltage across in forward bias, let's say this is the applied voltage. That's why across voltage means parallel voltage will have components in parallel. Because the voltage is same before the two components, that's why they are connected in parallel. Understood this? So RD and C diffusion are in parallel, are connected in parallel as same applied voltage is given to the diode. All right. Now second part, the next one, the last one. Let's draw the small signal model in reverse bias. So in reverse bias, what happens to RD? RD is very, very high. So it becomes open circuit, right? And what about C diffusion? C diffusion is negligible, right? So what is left out with? C depletion only, and which is given by epsilon A by W. This is also in picofarad. Very, very small. Okay. Now, next point is, you have written this much. Why it is not present in the forward bias? Because in forward bias, C depletion is negligible. Now, do you heard of RC delay? RC delay, time constant. Yeah. So this RC delay is nothing but time storage. This is the charge storage time. Okay. So under forward bias, RD, if you multiply it with C diffusion, what you will get? VT upon ID. And what was this formula? ID tau S into VT. What do you get? Time storage. Charge time storage. Yes. And now, if forward and reverse is separate, what for PN junction? No, no. Now we combine the entire model. So what do we get is this. RS will be present over here. Now remember, where will RS will come RS? So this is RD. This will be C diffusion. All of them are in parallel because same voltage is applied. This will be C depletion. This is P region. Now we also have to represent that series resistance. Now series resistance will not come in parallel, it will come in series. That RS is there, na? Neutral resistance, neutral region resistance. So this is the applied voltage. Applied voltage will be across this junction. So because of that series resistance, there will be IR drop. Let's say if a current flows through it, what will be this drop called as I into RS? So this will be the IR drop extra. This will be very, very small. This RS is less than 1 ohms. Still the IR drop will be very small, but it's there. So the applied voltage is dropped across this series resistance, and there are three elements over here: RD, C depletion, and C diffusion. All right. Yeah, very soon. Okay. So this completes module number 2.1. All right. Now let me give you the preview what is coming up now next. Okay. Next is metal semiconductor junction. I'll just give you a brief introduction to it and then we will go about it. So basically, if we have a PN junction, all right, now we are talking about the contact to the external world, this contact. We never talked about this contact, right? We just assumed that it's made up of some material, but this contact also plays an important role. So this contact can be ohmic or rectifying. Now, what is rectifying contact? What is ohmic contact? That is what we will see now in module number 2.2. Okay? This is P, this is N. All right? Now 2.3, what is 2.3? So we'll analyze these contacts. What is the role of a contact? This is my semiconductor, right? Now this semiconductor I have to connect it to external worlds via wire. So I need to have some contact. I cannot use any contact or a copper wire that cannot connect it to semiconductor. So we have to connect the proper material. So that's why we have a ohmic contact metal semiconductor. So this is metal, right? This is semiconductor. So metal semiconductor or MS contact we call it. Metal semiconductor contact can be ohmic or rectifying. A ohmic contact will have a characteristics which is looking like this, whereas a rectifying contact will have a characteristics which is looking like this. That's the difference. All right. Then we have heterojunction. Now, what is the concept of a heterojunction is as follows. So far we have assumed the PN junction. This is 2.3 heterojunctions. Just a preview of it, I'm giving it to you. What is upcoming for you all? So let's say if you have a PN junction, what we assume that it is made up of P silicon and silicon. What if these two materials are not same? What if it is silicon and this is germanium? It can happen, no? So this is called as heterojunction. Whatever we have studied so far about homojunctions, where P and N all were of the same material, but here it can be different materials. Got it? Now, next will be module number 3, which you already have some background in AEC, right? Bipolar junction transistor, but here we'll go in little bit detail. What do you call as transistor action? What is the structure? And we'll study in terms of energy band diagram. Now let's try to depict the energy band diagram of a, so this is module number 3, bipolar junction transistor. So we'll study everything with respect to energy band diagram. So you already know how the junction, this will look like. Emitter, base is the thinnest, and collector. Let's say for simplicity N, P, N. Now we have applied zero bias to it. We have not applied anything to it. Will there be a PN will there be a this thing formed, depletion layer? Yes or no? By default, no? Depletion layer will be by default. So what is this layer called as? Base emitter junction. What is this called as? Base collector junction. And now you know what we have to do? We have to determine the energy band diagram for it and the zero bias. So for that, we first consider, just give me a minute. We'll first consider a Fermi level which is constant throughout. Yes or no? And then what do we do? For N region, where is my conduction band? Let me concentrate over here. Where is my conduction band for N region? Near the Fermi level, right? This is EC. This will be EV. Agree? Same thing is happening over here also. Here also N region is closer, na? Here it is heavily doped basically. So here it will be little bit away. Like this. EC, EV. Why I've drawn away? Let me draw it symmetric first, or else you will want. I'll explain that later. Why I've drawn same? Because both are N region, na? Now P region mein, where is my this thing? Valence band? Near this, na? Actually, we should not draw up till here. We should leave some space for the what? Yes, that depletion region only. Here, this one. So this region up till here we have to draw. Right? And here also. So again I'm redrawing it. This is EC, this is EV, and this will be again EC and EV. Now where will my for the P region, where will it come? Yeah, it will be close to here, but where? From here to here, right? This is EV and this will be EC. Yes or no? And if I join together, this is how the diagram will look like. So this is the energy band diagram of NPN BJT under zero bias. Understanding? Now if we apply forward bias, what will happen to this junction? This junction, the depletion region is smaller. And this junction depletion region is larger. So this bending will be more, this bending will be less. It will be flatter. We have to study the entire BJT device under this energy band diagram. And later on we'll conclude that in this further. Later on we'll also see what is called as Abort-Small model, and hybrid PAM model already you are aware of. What is Abort-Small model is? Hybrid PAM model was valid for a small segment of an exponential curve. But this Abort-Small model will be valid for all the voltages. It's a universal model for BJT. So either large current or small currents, it supports everything. All right. And then we'll go for 3.2, which is HBT. Now what is HBT here? The material used was all silicon, right? HBT will contain different materials. So 3.2 will be heterojunction bipolar transistor. So over here, all the base material will be different. And that energy band diagram concept is entirely different. So this many more topics are left. These are very interesting. SBTs are normally used for high-speed devices. Yeah, once you understand the concepts are easy. But it's interesting to study something new which you don't know. BJT you know, but HBT you are not aware of. Neither heterojunction. So we'll look forward to complete that in the next class. The attendance sheet now I don't have it today. So you mark over here 19 and sign over here in the last column.